basically the term alpha comes from the fact that when we have this correlation, we're effectively producing some factor that is somehow giving us an edge in the market, and that can help us to make a bit of money. I mean, this cannot be traded as a strategy by itself, but it basically helps us in our research to tell us, hey, there is a possibility that this could actually make us some money. Now, there is, in fact, another way. So what we're actually doing right now is we're looking just at the correlation of two things. But what if something is actually related by a square law and it's not, in fact, linearly correlated? That could be a real problem if we use correlation. And for this, sometimes we use something that's called rank correlation, right? So let's just say we've got our XX, and then we could say our YY equals XX squared. Yeah. So if we plot this, we're basically getting a parabola. No, we're not, of course, because I only had one star here. That's obviously not squaring it. There we go. This is a parabola, right? And now we actually want this to be a relationship that is somewhat monotonous. So if it has two values for each x, the regression just won't work properly. So normally what happens is, let's just say we go xx equals np.linspace, say 0 to 20 in 200 steps. And then here we got this nice parabolic behavior, right? Now, if we wanted to basically do a linear fit of this, it's going to be terrible. If we do a linear correlation, we go mp dot coefficient xx, yy. There we go. Well, it's still got 0.96, but what it basically does is it fits like a straight line to this. And that's not necessarily ideal, because if we know that it's a square law, like we can fit it perfectly, right? And the correlation would be 1. And so if we don't know what the relationship is and we think it's maybe not linear, but we still want to see whether there is a good correlation, even without us knowing what the correlation is, there is something we can do. We can actually calculate what's called the rank correlation. Have you heard of that?
You mentioned it before, but not really.
Yeah. So this is really fascinating, because what we can do is we could basically sort the values of our x's and our y's, but instead of correlating the actual numbers of x and y, we're correlating the positions of x and y in the vector with each other. So let's just go, we've got x, and there's a function in Python called arcsort or numpy. Arcsort. Yeah. So if we had, like, say 4 values, the 0 value is the highest value, which is this. Yeah. Then the second value, which is number 4, is the second highest value. Yeah. And then this value here, right, correlates to the third, and so on, right? So this is basically how this is done. So 0 is a 10, then 2 is 4, 3 is 2, and 1 is basically 1. So it basically gives us the indices of the sorting. And so now if we have this, yeah, and we use the ranks, what we could do is basically something like this: plt.plot. And then instead of using x's and y's, yeah, we go mp.arcsort xx, yeah, and np.arcsort yy. And so if we plot this, what we're basically getting is a perfectly linear relationship. We don't even know what the relationship here is between x and y. It could be x to the power of 3, or it could be, let's say, square root x, or x to the power of 0.5, right? Like this. And yet, if we plot this, we still got a linear relationship. So what we can do is we can actually take monotonic relationships that are non-linear, and we reduce them to linear relationships by using the rank. We could also, if we had like X and Y not being in order and they would just be out of whack, that would still give you a linear slope. And I know it's a bit of a complex topic, but basically, when we do a correlation between a factor and the forward returns, we're generally assuming that this relationship is linear, but it's often not really linear. And so in this case, we really want to find something a bit better.